Yo, what's up, everyone? Welcome to the 2018 USNCO local exam States of Matter section. This is going to be from questions 13 through 18. Let's get started with question 13. What state of matter corresponds to the diagram below? In the diagram, you have a bunch of these molecules, and they're all of kind of different sizes. They all have different speeds, but you can see that they're all really spread out, and in general, their speeds are really, really high. This is going to be indicative of a gas. So remember, gas molecules are really spread apart. They move really fast, and they're always hitting against the sides of the container that they're in. That's what creates their pressure. Let's go to question 14. The normal boiling point of 2-propanol is 83 degrees Celsius, while that of acetone is 56 degrees Celsius. What is the principal reason for the greater boiling point of 2-propanol? The thing with the 2-propanol is that you have an OH here. In the acetone, you have a CO, and it's double bonded. But the thing with the OH is that since you have a hydrogen bonded with one of three highly electronegative atoms, fluorine, oxygen, and nitrogen, in this case we have oxygen, because of that you now qualify for hydrogen bonding. Hydrogen bonding is a really strong type of dipole-dipole interaction, and it really helps to improve to accentuate the intermolecular forces of a molecule. And that's going to be what's responsible for bringing up the boiling point. So which answer choice talks about hydrogen bonding? That's going to be answer choice D. So that's our answer. Let's go to question 15. Consider the four gases: carbon dioxide, nitrogen gas, carbon tetrachloride, and helium gas. What is the correct order of increasing average molecular speed at 100 degrees Celsius? Your average molecular speed is going to be your root mean square velocity. So your root mean square velocity is going to give you the speed of the gas, and it's equal to 3 RT over the molar mass of the gas. And this is in kilograms. What your root mean square velocity formula tells you is that as you increase your molar mass, the speed of your gas goes down. And the bigger your molecule is, the slower it is. So the fastest molecular speed is going to belong to the molecule with the smallest molar mass. So the one with the smallest molar mass is going to be helium, and so we can cross out A and C. The next, the one with the next least greatest molar mass is going to be nitrogen. So it's actually going to be answer choice B and not answer choice D. You can see that the rest of them are also in order of molecular weight. So yeah, it's going to be, the answer for 15 is B. Let's go to 16. Under what conditions will the behavior of an ideal gas best approximate the behavior of under what conditions will the behavior of a real gas best approximate the behavior of an ideal gas? 1, high temperature, 2, high pressure. Remember, an ideal gas is a gas that's moving really, really fast. If it moves really fast, it kind of avoids all the intermolecular forces. And also, a ideal gas is going to have really low pressure. The reason for this is because we assume the volume of a gas particle to be negligible, to be zero. So when it hits against the sides of the container, it shouldn't really have any effect on the container. So we want one, really low pressure, and we want high temperatures. High temperatures are going to make it so that the molecules themselves don't really interact much. They're way too fast for them to form intermolecular forces. So we want high temperature, low pressure. So that's going to be just 1. So our answer is A. Let's go to question 17. A solid has a melting point of 1710 degrees Celsius, is soluble in water, and does not conduct electricity in the solid state. What is the most likely nature of the bonding in this solid? This is screaming of ionic bonding. Ionic solids have really high melting points, which we see here. They are soluble in water, and the thing about an ionic solid is that they don't conduct electricity in the solid state. They make sure to mention the solid state because in an aqueous state, the molecules do conduct electricity. The reason for this is because when you have an ionic solid, such as like sodium chloride, all of these molecules are ionically bonded, meaning their ions are trapped in these bonds. But what happens is that when you put them in some sort of solution, when I take them and I put them in some sort of solution here, and they break up into their cations and anions, what that's going to allow for, and I'll just finish drawing them here. I'm sorry. What that's going to allow for is that their electrons are now freed up for movement. Their electrons can now move, and that is all we need to conduct electricity. So when you have your solid form, the electrons are stuck within the bonds, but when you dissociate, when you go into your aqueous form, the electrons are now free to conduct electricity. And that's characteristic of ionic bonding, so that's answer choice C. Let's go to question 18. So toluene C7H8 has both a higher vapor pressure than water at 25 degrees Celsius and a higher normal boiling point. What statement best describes these observations? Let's go through our answer choices. So A, liquids with higher vapor pressure typically have higher boiling points. That's usually not true. If a liquid has a higher vapor pressure, then it's going to be easier for that liquid to reach a vapor pressure that's equal to atmospheric pressure. When the vapor pressure of a liquid is equal to the atmospheric pressure, that's when you've reached the boiling point. So if your vapor pressure is naturally high, it usually requires less energy for you to reach your boiling point. B, toluene has a higher molar mass than water. That's not really going to affect much. C, toluene has a lower heat of vaporization than water. This is going to have some sort of impact. And this is going to come from the Clapeyron equation. So it's the natural log of the second pressure over pressure 1 is going to equal the negative enthalpy of vaporization over R times 1 over T2 minus 1 over T1. This equation is a fancy way of saying that as you increase your temperature, your pressure is also going to change, and it's going to depend on your it's going to depend on your heat of vaporization or your change in enthalpy of vaporization. Since toluene would have a lower heat of vaporization, if you graphed your pressure versus temperature graph, the graph for toluene would actually have a lower slope than your water. So toluene might look something like this, and let me just mark it. And water might look something like this. So water has a higher slope. And the reason that this is helpful is because it explains why you would have a higher normal boiling point. At a given pressure, after our intersection point, at a given pressure, if you look at the point at which you intersect with the water line and the point at which you intersect with the toluene line, the water line is going to be at a lower temperature than the toluene line. So this means that at atmospheric pressure, your toluene line is going to be at a greater temperature. This means your boiling point is higher. A lower heat of vaporization also explains why you have a higher vapor pressure. It takes less energy for the liquid to turn into gas. That's why you have more of this vapor, you have greater vapor pressure. So C does make sense. Let's just make sure D is wrong. The density of toluene vapor is greater than that of water vapor. That's not going to really mean much. That doesn't explain why you would have a higher vapor pressure or a higher normal boiling point. So our answer is C. All right, that's all I have. I hope this was helpful. I hope you were able to learn something, and I hope to see you later. Thank you.